Calculus 1 was all about differential calculus. In other words, given a function, how do we understand what its rate of change is with respect to the independent variable? If you have the position of your car as a function of time, how do you use that information to figure out your velocity? If you have your velocity, how do you use that information to determine your acceleration? If you have the salinity of seawater as a function of depth, how do you measure or how do you analytically describe the rate of change of the salinity with respect to a rate of change of the increasing depth? So if your depth increases by 1 unit, by how much will your salinity change? Calculus 2, on the other hand, seeks to ask the opposite question. So given a rate of change, how do you determine your total cumulative change over a period? So if you have your velocity as a function of time, how do you measure how far you've gone? If you have the mass flow rate of water through a pipe, how do you figure out how much cumulative water has passed through that pipe, given its mass flow rate as a function of time? Now, the main gateway that connects the two subjects, we can view as the concept of antiderivatives. So antiderivatives are basically doing the opposite of what you did when you took the derivative. So you have a function, you take the derivative. This time we're going to start with the function and figure out its antiderivative. Now the antiderivative is just the opposite of the derivative. So if the derivative takes you a step down, the antiderivative takes you a step back up. Once we understand antiderivatives, we'll begin discussing kind of the heart of calculus 2, or integral calculus, which is the definite integral. But first we have a basic notation, and that is the concept of an antiderivative. So given a function f, we'll say f of x, an antiderivative of f is a function which we'll call capital F of x, whose derivative is little f, i.e. capital F prime of x is equal to little f of x. Right, so basically when you start off with a function and you say, well, what's the antiderivative of this function? What you're asking is, find another function whose derivative gives you the function you're looking at. So it's basically working backwards. So since you know a bunch of derivative rules, you just have to think about those rules backwards. So starting with the derivative, how do you get back to the original function? It's the same question as saying, starting with a function, how do you get to its antiderivative? Now there are a few things to note. First is that I used the word an here. So an antiderivative of f is a function capital F of x whose derivative is little f. So this implies that there is not just one antiderivative. So it's not the antiderivative of f, it's an antiderivative of f. So the first thing to note is that an antiderivative is not unique. So in other words, one function will have multiple antiderivatives, if it has any. And the second point is that not all functions have antiderivatives. So let's write this out. So not all functions have, and let me write simple antiderivatives. So it's not always possible, as was the case with derivatives, that we could write out the answer in terms of elementary functions in a finite number of terms. So given any of our basic functions, we were always able to find the derivative and express it in terms of other elementary functions. Derivative of sine is cosine, and so forth. For example, e to the x squared doesn't have a simple antiderivative. There's no way of writing this in terms of e to the x squared divided by 2x or anything like that. There's no simple way of writing it. Now, you can say that it does. There are functions out there that you can define to be the antiderivative, but you just can't express them in terms of elementary functions. You can write an infinite series expansion for this, for example, which we will do later in the course. But in terms of elementary simple things, not all functions for that purpose have antiderivatives. So we're looking at functions, and some functions have these antiderivatives available to us. Now, the first basic theorem about antiderivatives is the following. So theorem, suppose that capital F of x and capital G of x are antiderivatives for the function little f of x. Then capital F of x is equal to capital G of x plus c, where c is some real number. In other words, whenever you have two antiderivatives for a given function, they are always related to each other by a constant, right? So this answers the question, well, are there other antiderivatives? Suppose you find one antiderivative and you have a nice expression for several antiderivatives of a function. You might ask, well, is this all that there is? And the answer is yes. So what this says is that once you find one antiderivative, any other antiderivative that you can possibly find is just a constant added to that first antiderivative. So up to an additive constant, antiderivatives are in fact unique, right? So you can have two antiderivatives for the same function, but they have to be related to each other by an additive constant. So let's see an example. Suppose that f of x is equal to 2x. Well, this should be pretty simple to work out. We're looking for a function capital X whose derivative is 2x. Well, the answer is going to be x squared, right? The derivative of x squared is 2x. But your friend says that his antiderivative is x squared plus 18. Well, he's right too. The derivative of x squared plus 18 is also 2x. Notice that the two different antiderivatives, well, they're different antiderivatives, but they're just related to each other by an additive constant. And maybe somebody else comes along and says that his antiderivative is x squared plus 222. Okay, well, the derivative of 222 is 0, so x squared plus 222, the derivative is still 2x. So these are all correct antiderivatives, and they're all related to each other by just an additive constant. To prove this theorem, what we can do is, well, since capital F and capital G are both antiderivatives of little f, that means that, so we'll say proof, capital F of x has to equal little f of x, because by definition, capital F is an antiderivative of little f. And we also saw that capital G of x is an antiderivative of little f, so that means the derivative of capital G is equal to little f of x. Okay, so the derivative of capital F is little f of x, derivative of capital G is little f. So how can we use this to prove that capital F and capital G are related to each other by a constant? And the trick is to introduce a new function. So let's call it h of x equal capital F of x minus capital G of x. Okay, well, what's the derivative of h? Well, the derivative of capital H is going to be the derivative of capital F minus the derivative of capital G. But since capital F is an antiderivative for little f, its derivative is just little f. Similarly, since capital G is also an antiderivative of little f, the derivative of capital G is also little f, which means that the derivative of capital H is just equal to 0. Now, when you have a function whose derivative is 0, what does that imply? That implies that h of x is some constant function, so it's just equal to a constant. The h of x was capital F minus capital G, which means that capital F minus capital G is a constant. Ergo, capital F of x is equal to capital G of x plus c. So once you find one antiderivative, you basically have all of them, because all antiderivatives for a given function have to be related to each other by a constant. Now what does this look like graphically? Recall that when you add a constant outside of a function, it represents a vertical shift or a vertical translation. So if we have the graph of capital F of x, so suppose this is an antiderivative for some function little f, well, every other antiderivative is going to look exactly the same, except it's going to be related, except it's going to be shifted up or down by a constant. So this might be capital F of x plus 3, capital F of x plus 6, capital F of x minus 3, and these would all be antiderivatives for little f of x. There are some imperfections in the way I drew it, but there's literally it's just supposed to be, take the graph, you pick it up and slide it up or down, just like that. So it's the exact same graph, except it's shifted either up or down. So all antiderivatives will, for a given function, will be related to each other in that one particular way.